Once we understand how X-rays are produced, we must also understand the factors that control production. With the advent of digital radiography, evaluation of an image and correlating that image with relative radiation doses changed. In the film screen error, the evidence of either too little or too much radiation used for a given exposure was clear. Use the wrong amount of radiation and the resulting exposure was too dark or too light and required a repeat of that image. With digital radiography, underexposure is easy to determine because the image is noisy or displays a grainy appearance called quantum model. As radiation amounts increase, the image becomes smoother in appearance until radiation amounts become so high that the blacks and grays merge with the background and eventually become indistinguishable from that background. At this point, the image becomes saturated and must be repeated. Modern digital imaging systems can correct for about 8 to 16 times overexposure from the optimal range. For the digital radiographer, the question becomes, how do I produce an image that demonstrates disease or injury but keeps the relative radiation dose as low as possible? To address proper exposure question, radiographers must constantly be aware of the amount of radiation used for any exposure and the penetrating power of that beam. To begin, let's discuss milliamperage, or as it's better known, mA. mA is short for milliampere, an electrical measure that indicates the electron flow in a circuit. In the X-ray tube, mA measures the number of electrons flowing from the cathode to the anode per second. Furthermore, mA indicates the rate of radiation flowing out of the tube on a per second basis. It is important to understand that knowing mA alone does not determine the radiation amount. Since mA indicates radiation flow, it alone will not determine the amount of radiation used in a given image. So simply stated, mA controls the rate of radiation production. Here we have two X-ray tubes. Now let's start an exposure with the first tube on the left, then the tube on the right, and compare the X-ray beams. Notice the beam on the right contains twice the number of X-ray photons to the beam on the left. The beam on the left represents 100 mA exposure, and the beam on the right indicates a 200 mA exposure. It should now be apparent that knowing just the exposure rate, the mA value does not contain enough information to determine relative dose or total radiation exposure to the image receptor. Exposure time must be considered. To breach the gap, the concept of milliampere second was conceived. If I ask the question, how much radiation did I produce? mA provides only half the answer. To answer the dose amount question, we need to also factor in the exposure time. Let us repeat the previous example with an additional twist. We will fire the two X-ray beams for a set amount of time. The beam on the left will expose the image receptor for exactly 2 seconds, and the beam on the right for exactly 1 second. When we compare the effects of the two exposures, an interesting result is observed. Even though the exposure on the right produces radiation at twice the rate, both exposures have equal effect on the image receptor, and the patient dose is equal. This is because the beam on the right produced radiation at twice the rate for half the time when compared to the beam on the left. This leads to a math calculation. The rate of radiation production multiplied by the time of exposure produces a number that indicates the total exposure and provides information regarding the relative dose the patient received during the exposure. More simply put, mA multiplied by time equals mAs. You will notice that there are multiple ways one can produce a 20 mAs exposure, and I'm sure the generators at your hospital will produce even more variation. In the table on the left, notice how the mA exposure time can be manipulated to achieve successively higher radiation doses. Each dose is twice the previous dose. For some, the doses are doubled by manipulating the mA, others by time. In the second table, notice that wildly different mA and time values are used to produce the same effect. Without some record of the exposure factors used, no one would be able to tell which set of exposure factors was used to produce the image, because all images are exactly identical. Competent radiographers can calculate or estimate mAs values without the aid of external devices or written tablets. The image below represents a basic X-ray machine control panel. This panel has rocker switches to increase or decrease settings and a display area that shows the current settings. Not all X-ray control panels will display mAs. In this case, calculations become responsibility of the technologist. On this panel, an 800 mA using 20 milliseconds time setting will produce an mAs of 16. Should the image need to be repeated due to an exposure error, knowing the mAs used will aid you and the radiographer in making an informed decision of how to produce an accurate correction. Knowing mAs can aid you in determining what amount of radiation to use for future examinations. For every examination, a competent radiographer will know the mAs needed to make every exposure. This calculation provides information of how to correct an exposure should an error be made. If you are wondering what makes an incorrect digital exposure, it is an exposure that deviates from the manufacturer's recommended exposure range. When deviation occurs, the competent radiographer will know how to correct the problem and follow the manufacturer's recommendations for maximum dose as indicated by the S number, the EI number, or the LGM. Whether or not your equipment supplies mAs calculations, the responsibility is yours to calculate the mAs before pressing the exposure switch. Thank you.